Nearly 2,000 years ago, the Roman philosopher and scientist Ptolemy tried to explain how light bends as it passes from one medium to another. In a treatise on optics, he described a trick of light which you can easily repeat today. Ptolemy put a bowl on a table. Inside the bowl he placed a coin. Then Ptolemy lowered his eye until the coin was no longer visible over the rim of the bowl. The next step was to pour water into the bowl. As the water level rose in the bowl, the image of the coin became visible. We call this refraction, the bending of light as it passes between two transparent substances. An incident ray from the object, the coin, strikes the surface of the water. The refracted ray changes direction to reach the eye. The image of the coin lies on the extension of the refracted ray back into the liquid, even as the coin object itself lies out of line of sight to the eye, below the lip of the bowl. In the year 1621, Willebrord Snell identified a link between the path of light entering a transparent substance and the changed path of light within the substance. From a line normal or perpendicular to the surface of the substance, Snell measured his angle of incidence. The angle of refraction was also measured from this normal line. It's important to note that the angle of incidence, the normal line, and the angle of refraction all lie in the same plane. Snell found that the sine of the angle of incidence divided by the sine of the angle of refraction is a constant number. We now know that if the medium which the light is leaving is either air or a vacuum, then that constant number is the index of refraction for the substance which light is entering. For example, for light leaving air and entering water, the sine of the angle of incidence divided by the sine of the angle of refraction will equal 1.33, the index of refraction of water. This provides a direct link between the speed of light in both substances, because the index of refraction is nothing more than a ratio of light speeds. It also gives us a way of calculating the speed of light in an unknown substance. A light ray enters the crystal and refracts. Measure the angle of incidence and the angle of refraction. Use the sine of these two angles to calculate the index of refraction. That mineral can be identified from tables of refractive indices. And since the refractive index is a ratio of light speeds, we can determine the speed of light in this substance. When a ray of light passes from one substance to another, and neither of these is air or a vacuum, Snell's observation still holds true. Light passing from water into glass, for example, produces a constant of 1.12. This value is neither the index of refraction of water nor of glass. Instead, it is the ratio of the two indices. This relationship between the angles of incidence and refraction is known as Snell's law, and is usually expressed this way. The product of the index of refraction of the incident medium and the sine of the angle of incidence is equal to the product of the index of refraction of the refracting medium and the sine of the angle of refraction. When light travels from one transparent substance into another, Snell's law accurately predicts how light will refract. But the obvious bending of light at the surface of a substance is not the only effect of refraction we can notice. Consider this bottle brush sitting in a beaker. When viewed from the side, through the beaker, it appears to be discontinuous. The fraction of the brush we are viewing through the beaker is displaced to one side. How does this happen? Let's look at the simplest case, replacing the beaker with a block of glass to avoid the more complicated mathematics of multiple materials seen through curved surfaces. A light ray from the bottle brush first passes through air and into the glass, where it refracts, according to Snell's law. The dotted line represents the path light would take towards the eye if it did not refract. If a line is drawn normal to the surface at the point of contact, we can measure an angle of incidence between the normal line and the light ray. Since the ray is leaving a less optically dense medium and entering a more optically dense medium, the angle of refraction relative to the normal is always less than the angle of incidence. In other words, in this situation, the refracted ray always bends towards the normal. When this refracted ray strikes the other side of the glass, it will do so at a point closer to this normal than it would have if there had been no refraction. What happens now is the light ray leaves the glass. Snell's law holds equally true for light moving from a more optically dense medium, glass, to a less optically dense medium, air. Again, draw a normal line at the point where the light moves from one medium to another. Compared to the angle of incidence, in this situation, the angle of refraction will always be larger. In other words, the light ray always refracts away from the normal line. How much does it bend? Play with angles of incidence and refraction, and Snell's law will quickly demonstrate to you the principle of reversibility of refraction. Light enters a medium with a particular angle of incidence, which produces a particular angle of refraction. If that same angle becomes the angle of incidence of light leaving the medium, then it will refract back along the original angle of incidence. But in our case, the light is not hitting a mirrored surface and returning exactly the way it came. Instead, it continues on to strike the opposite surface of the glass. Since the two glass surfaces are parallel to each other, so are the normals at the point of entry and exit. Geometry can prove that the angle of refraction on entry is equal to the angle of incidence on exit. According to the principle of reversibility, it means that the angle of refraction back into the air will equal the original angle of incidence from the air. The light ray originating from the bottle brush and entering the glass is in fact parallel to the light ray leaving the glass towards the eye. But it has been displaced along the surface of the glass. The eye sees the object itself above the glass, along this line. But thanks to the double refraction of light into and out of the glass, an image of the object appears behind the glass along this line. This very simple displacement of an object by refraction illustrates the principle of reversibility of refraction and depends on a glass block with sides that are perfectly parallel to each other. So, what happens when these sides are not perfectly parallel?